In this video, we're just going to have a quick look at what happens to our code when it's assembled and how we interpret the information that we're given. Okay, so here I've got some basic code. We're just doing some addition, some subtraction, some loading. It doesn't really matter too much about the instructions at the moment. We've got a couple of labels here. They're not tremendously useful. I just want to show you what happens to your labels when you assemble them. Okay, so let's save this and then assemble our code. And it takes us to this screen. Okay, so what's happening here? Well, this is our source code here. This is all of the instructions that we just wrote. So nothing should change here. This should just be what you've done and left as it is. The next column is called the basic column. Now this converts what are known as pseudo instructions into instructions that can actually be carried out by the assembler. So you'll see here that add immediate is unchanged other than converting the number that we've given it into hexadecimal. That's because we use hexadecimal here. It needs to be something that it can understand. And then you can see in the next line we've got subtract, and I've given it a hard value of 50 here. Now if you've seen the other video, you'll know that I said to do arithmetic using MIPS we need to have values stored in registers. We can't just go out and do it, with the exception of add immediate. So what the assembler has to do here is say, well, I can't do subtraction unless these values are stored in register. So how do I make that happen? Well, it takes our hard-coded value of 50, it converts it to hexadecimal, and then it adds it together with 0 and stores it in a new register. So why does it add it to 0? So that it doesn't change the value that we've given it, and that really just means that add immediate becomes a store instruction. So it stores it in a register, in this case register 1, and then it performs the subtraction instruction with the new register and the old register. So that's the assembler doing a little bit more work than you're thinking it should do. It's converting it into something it can understand. And let's have a look at load immediate, because load immediate is actually a pseudo instruction. Now, what is a pseudo instruction? Well, in MIPS, the instruction set is very small. We don't have that many instructions to use. So we might want to build a more complicated expression out of simpler ones, and that's what a pseudo instruction is. It's an instruction that doesn't actually exist in the instruction set, but has been built out of ones that do exist. So load immediate here is just saying store the value of 50 into register T2. And the basic column, what it's doing is it's adding the immediate value. Again, it's converted this 50 into hexadecimal here, and it's adding it with 0 into a register. Again, we add with 0 so that we don't change the value, but this is really the assembler using add immediate as a sort of storage instruction rather than this load immediate that doesn't really exist. So that's what the assembler does here. This is it just converting it to what it understands. And you can see add here is just left the same. The register names are given their actual numbers rather than the names that we use. But yeah, it's left the same because it's an instruction that exists. It's been given 3 registers as it requires, so nothing needs to be done to make it work. Now the next column here is the code column. Now this is the machine code instructions. This is our code has been assembled down to machine code, which the CPU could then actually execute. So that's all this is. We don't need to understand this. Machine code is not human readable, so that's fine. That's just so you know what it is. And then we have the address columns. Now you'll notice that it always stores it in this address first, this 0040000. And then the next instruction is always stored 4 spaces on. That's because to store a word we need 4 register spaces, because each register stores a byte and a word is 4 bytes long. So that's why we increment by 4, not by 1. So all of the instructions are given an address and stored there. So if we go over here to our labels, and if you'll remember the code was at the very start, it's got the same address as our first instruction, and the end, which was just after our instructions, is stored 4 registers on from our last instruction, as it should be because it was after our code. And these boxes here are breakpoints. Now what they allow us to do, if I tick this, it will run through the code and stop at this position. So let's do that. And this is useful for the purposes of debugging and so on. Okay, so that's everything I wanted to cover. The main takeaways are that our code doesn't stay the same. We need to convert pseudo instructions. We need to convert instructions like sub here, which aren't in the right format, into something that can be executed. And then it's assembled down to machine code, and it's given an address to store it at. So that's everything for today. I hope you found this useful. If you do have any questions, feel free to get in touch. Thanks.